Hello everyone, welcome to the third video of the series Basic Organic Chemistry. So today we are going to learn about nucleophiles. The term nucleophile can be divided into two parts. One is nucleo, second one is phile. Nucleo means nucleus, phile means loving. We all know that nucleus is positively charged. That's why a nucleophile is a species which loves positively charged nucleus. In order to love positively charged nucleus, nucleophile should have the opposite charge. What is that? Negative charge. Therefore, we can say nucleophile is a negatively charged species, or it could be a neutral molecule which is rich in electrons. The same thing is given here. So nucleophile could be a neutral molecule having lone pair of electrons. Examples are given. H2O that has oxygen which has two lone pairs. Then ammonia which has nitrogen with one lone pair. ROH is alcohol, again oxygen with two lone pairs. Now this compound is dimethyl sulfide or DMS. Here sulfur has two lone pairs. Now this compound is triphenyl phosphine. Three phenyl groups, that means benzene rings, are attached to phosphorus. So phosphorus has lone pairs. So these are all examples for neutral nucleophiles. We can also have negatively charged nucleophiles or anions. Examples are hydroxide, OH minus, halide, X minus. It could be iodide, bromide, chloride, fluoride. Then alkoxy group, RO minus, etc. Since nucleophiles are electron rich, they always attack electron deficient species. Now what are electron deficient species? They are nothing but electrophiles. So it can be shown like this. Here we have a nucleophile with lone pair of electrons. This is an electron deficient electrophile. So nucleophile attacks electrophile and a new bond is formed between nucleophile and electrophile. When a new bond is formed, nucleophile is donating electrons to electrophile. For that reason, nucleophile now becomes electron deficient, so positive charge on nucleophile. I hope it is clear to you. Now we have a term called ambident nucleophile. See, in all these examples, we saw one attacking atom, oxygen, halogen, nitrogen, sulfur, right? In all these examples, there was only one attacking atom. If the nucleophile has more than one suitable atom through which it can attack the substrate, you call it as ambident nucleophile. Generally, ambident nucleophiles have two attacking sites. For example, cyanide, Cn minus, here carbon and nitrogen, both of them have lone pair of electrons. That's why there are two attacking sites. It can attack the electrophile either with carbon or with nitrogen. Then we have isothiocyanate, that is SCN minus. Here also sulfur and nitrogen. Then we have nitrite ion, NO2 minus. Nitrite ion can attack either through nitrogen atom or through oxygen. There is one more example for ambident nucleophile, that is DMSO. Here is the structure, dimethyl sulfoxide. From the formula itself you can name it, dimethyl sulfoxide. So dimethyl sulfoxide has oxygen and sulfur both with lone pair of electrons. And if you try to methylate this DMSO, that means if you try to add methyl group to this compound with methyl iodide, you will get two isomers A and B. One will be because of S-methylation, that is methyl group added to sulfur. Second one is O-methylation, that means oxygen attacking the methyl group. We know that sulfur is a better nucleophile site than oxygen. What is the reason for that? Among sulfur and oxygen, oxygen is more electronegative. Correct? No? So electronegativity means what? Ability of an atom to attract electrons towards itself. Now what is nucleophile? Nucleophile is nucleus loving species. It should love positive charge. Oxygen is more electronegative. That means it attracts negatively charged electrons towards itself. That is why, since sulfur is less electronegative when compared to oxygen, sulfur is a better nucleophilic site. That's why we can say the product which involves S-methylation will be the major product. We will see the reaction. Here we have dimethyl sulfoxide, CH3 twice S double bond O. When it undergoes methylation, with methyl iodide, we will get two products. One is because of S methylation. So sulfur attacks on methyl group. So we get methyl group, third methyl group attached to sulfur. CH3 thrice S plus double bond O, which is stabilized by iodide ion. Since sulfur is donating electron to methyl group, S becomes plus here. Plus one more product is possible, that is oxygen attacking the methyl group. See students, it can be shown like this. Oxygen attacking methyl group. At that time methyl iodide bond breaks like this. So CH3 gets attached to oxygen. We get something like this, O plus CH3 double bond S CH3 CH3. But since oxygen is highly electronegative, positive charge on oxygen is not stable. So this pi bond shifts like this. So we get CH3S CH3 OCH3. But since pi bond has shifted, sulfur develops positive charge. So the same thing is given here. CH3 twice S plus OCH3, that is stabilized by iodide ion. I hope this reaction is clear to you. Now, as sulfur is more nucleophilic than oxygen, the first product, that is S-methylated product, is the major product. Next topic is strength of a nucleophile. A nucleophile is a thing which loves positive charge. You know that, right? So, if the nucleophile has high electron density in it, then it will definitely be a better nucleophile. Correct? No? So, nucleophilicity of a species increases with increase in electron density. Therefore, we can say a nucleophile with negative charge is stronger than its conjugate acid. Let's take an example. We all know that alcohol is the conjugate acid of alkoxide ion and water is the conjugate acid of hydroxide ion. Since nucleophile with negative charge is stronger than neutral molecule, alkoxide is more nucleophilic than alcohol. Similarly, hydroxide is more nucleophilic than water. So if a question comes that among CH3O minus and CH3OH, that is methanol, which one is more nucleophilic? The answer will be methoxide ion. Next point, along the period, that means in the periodic table from left side to right side, the nucleophilicity decreases with increasing atomic number of the atom having negative charge. Let's take an example. Cr3 minus is more nucleophilic when compared to Nr2 minus. That is more nucleophilic when compared to Or minus. That in turn is more nucleophilic than fluoride ion. Now what is the reason for that? It is simple. Along the period, size of the atoms decreases. Correct, no? So carbon has larger size when compared to fluoride. As the size decreases, the electronegativity increases from left to right. Electronegativity means ability of an atom to attract negatively charged electrons towards itself. Nucleophilicity means what? Its ability to love positive charge. We are interested in nucleophilicity here. That means ability to get attracted to positive charge. So, the atoms which have high electronegativity are less nucleophilic when compared to atoms with low electronegativity. I hope it is clear to you. When same atom is attached to different groups, how does nucleophilicity vary? So here is an example. Alkoxide greater than hydroxide, that is greater than carboxylate, which in turn is greater than alcohol, that is greater than water. Let's divide this into two parts. The first part has negatively charged ions, second part is neutral molecules. As we studied earlier, nucleophile with negative charges more stronger than neutral molecules. And among these three, why is alkoxide more nucleophilic? It is simple. R group shows positive inductive effect, that means electron releasing property. So these are electron rich. RO minus is more electron rich when compared to hydroxide. Oxygen attached to alkyl group is more electron rich when compared to oxygen attached to H+. But if you take this example, here we have electron withdrawing carbonyl group. That is why it is less nucleophilic when compared to hydroxide. Then we have the neutral molecule alcohol. Here, oxygen is attached to one hydrogen and one alkyl group. As we studied, alkyl is electron releasing. So it is more electron rich when compared to water, in which oxygen is attached to two hydrogen atoms. So these type of trends are very important in the exams. Next trend, what happens to nucleophilicity down the group in the periodic table? Down the group, nucleophilicity increases with increasing atomic number. Let's see the reason for that. Since we are talking about nucleophilicity, you don't have to consider the left side of the periodic table, which has electropositive atoms. So let's consider the right side of the periodic table. Okay, so let's consider anions here. Now, why is nucleophilicity increasing down the group? Let's see the reason. There is a concept called solvation. Solvation means what? In the solvent, the ion is surrounded by solvent molecules. That process is called as solvation. So solvation of an anion, that means anion getting surrounded by solvent molecules, helps to stabilize the anion. Okay? So when it becomes stable, it will lower its nucleophilicity. If the anion is in a stable, nice condition, it will not prefer to attack a positive center. Okay, so we can say solvation stabilizes anion. That's why it reduces its nucleophilicity. Now there is a concept called polarizability of an anion. What is meant by that? Here we have an anion and a cation. Okay. Now polarizability of a nucleophile is related to the ease with which valence electrons of the anion interact with the nearby electrophile. Okay. If the atom is very large, the outer electrons will not be under the control of central nucleus. Correct, no? That means outer electrons can easily attack the cation. In that case, polarizability of that anion is more. So I can say larger atoms or ions are more polarizable than smaller ones because outer electrons are not under much control of the nucleus. One more thing is, if the nucleophile has very large size, then it is weakly solvated. That means it is not stabilized by solvation. And such a large nucleophile will be more polarizable than smaller nucleophile. Therefore, we can say large nucleophiles or the nucleophiles which have larger attacking atoms are better nucleophiles. So we were discussing this. Down the group, nucleophilicity increases. The reason is down the group, size of the atom is increasing. Because of solvation and polarizability, larger nucleophiles are better nucleophiles. The example is given here. If you consider 17th group where we have fluorine, chlorine, bromine and iodine. Iodine is having the largest size. That's why iodide is more nucleophilic than bromide. That is more nucleophilic than chloride, which in turn is more nucleophilic than smallest fluoride. Similarly, if you take Rs minus and Ro minus, sulfur has larger size than oxygen even though both of them belong to same group. Since sulfur is larger than oxygen, Rs minus is better nucleophile when compared to Ro minus. Similar is the case with nitrogen and phosphorus. R3P is more nucleophilic when compared to R3N. Finally, one small topic, nucleophilicity versus basicity. Nucleophilicity of a reagent might perhaps be related to basicity, but it is not always true. For example, methyl mercaptide. Mercaptan means sulfur. Okay, methyl mercaptide, that is CH3S minus, is more nucleophilic than methoxide. Just now we studied sulfur has larger size than oxygen. That's why sulfur is more nucleophilic than oxygen. Even though it is the case with nucleophilicity, CH3S minus is a weaker base when compared to CH3O minus. The reason is simple. What is a base? One of the definitions of base is a base is a substance which is a proton acceptor, H plus ion acceptor. Since oxygen is more electronegative when compared to sulfur, methoxide is a good base when compared to methyl mercaptide. Therefore, the conclusion is not always nucleophilicity of a reagent is equal to basicity. So students, that was about nucleophiles. I hope this topic is clear to you. The screenshots of the same will be provided here. I hope it is clear to you. Thank you so much for watching.